Section 5.3 is the most challenging part of the probability unit, so I suggest that you read and study the examples carefully in Section 5.3. Conditional probability is something we've worked with before but haven't officially defined. Conditional probability is the probability that one event happens after another event is known to have already happened. Suppose we know that event A has already happened, or is the given information. Then the probability that event B happens, given that event A has already happened, is denoted by this notation. B, with the probability of B given A, has a kind of this vertical line here. Probability of B given A. So for example, if we know that a randomly selected student has pierced ears, that's our given, that's the event that has already occurred. What is the probability that the student is a male? So we look at only the people with pierced ears. So I've circled that in blue. So we write this, the probability that the person is male, given that they have pierced ears, or the probability of M/E, which is the pierced ears. So among all of those that have pierced ears, 19 are males, so we write 19 over 1 over 3, which is 0.184. And usually it's good practice to write then the probability in a sentence. 18.4% of students who have pierced ears in this sample are male. What is the probability that a randomly selected male student has pierced ears? Now this is the opposite conditional probability. This is not the same thing. This is saying that our given now is that the student is male. That is the event that has already occurred, and then we want to know what's the probability that among that group someone has pierced ears. So we look at all the males. 19 out of 90 would be the answer to this one. That's about 0.211. So we say 21.1% of males in the sample have pierced ears. Now looking again at number 1, what we did was we looked just at the chart and we said the probability of male given that they have pierced ears is the number of students who are male and have pierced ears over the number of students with pierced ears, 19 over 103. But what if we focus on probabilities instead of the number of students? So what if we say the probability that a student is male and has pierced ears is 19 out of 178, and the probability that a randomly selected student has pierced ears is 103 out of 178. This still reduces to 19 over 103, but it allows us then to write the probability as this statement. The probability of M given E is the probability of M and E over the probability of E. This is shown on the AP formula sheet using the letters A and B instead of M and E. So the probability of B given A is the probability of A and B over the probability of A. So the given becomes the denominator. The probability of the given is the denominator, and then the probability of the numerator is that A happens and B happens together. This could also be rearranged to do what's called the general multiplication rule. The general multiplication rule says that the probability of A and B equals the probability of A times the probability of B given A. So the probability of A times the probability of B given that A has already happened, multiply those together, and that's the probability that both of them happen. Now personally, I never use the general multiplication rule, and here's why. If I go back up to this chart and look at this particular situation, the probability of female and pierced ears. So if we go up to the chart, well, that's pretty obvious. The probability that someone is female and has pierced ears is 84 out of 178. But if we apply the formula, we would say the probability of female and pierced ears is the probability of female times the probability that they have pierced ears given that they're female. So the probability of female, looking up the chart here, you can see The probability of female is 103 out of 178. I'm sorry, that's pure steers. The probability of female is 88 out of 178. The probability of pure steers given that someone is female is 84 out of 88. So when we multiply the two together, the 88s divide out, and we have 84 over 178, which is a lot of extra work for something that we could see obviously just by looking at the chart. Now there are a very few situations where maybe this formula would come in handy, and that's maybe when you're given less information and all you know are these two pieces of information. So there's an example on page 322 where that happens. So it says, the Pew Internet and American Life Project find that 93% of teenagers ages 12 to 17 use the Internet, and then 55% of online teens have posted a profile on a social networking site. Find the probability that a randomly selected teen uses the Internet and has posted a profile. Show your work. Well, we know that the probability that they're online is 0.93, and the probability of that they're on have a profile given that they're online equals 0.55. So basically we're saying 55% of the 93% have profiles. So it makes sense that we multiply those two together. The probability of online times the probability that they have a profile given that they're online is the probability that they are online and have a profile, which is about a 51% chance. However, other than a situation like this, I prefer just to read the probability right off of the chart.